All right, let's talk A-level physics. You know, you've wrestled with quantum mechanics, you've navigated gravitational fields, but for so many of us, the real headache comes down to three little things: uncertainties, significant figures, and decimal places. It's always the same questions, right? When do you use which one, and why does it feel like every teacher gives you slightly different advice? Well, that's what we're going to tackle today. Let's create the definitive guide you've been looking for.
And look at this, a post from a student on Reddit that just perfectly nails that feeling. If you've ever felt this way, trust me, you are definitely not alone. So think of this explainer as the answer to that post. We're going to make it clear, direct, and really focus on getting you those crucial marks on your practical papers.
So here's the game plan. We'll start by looking at that student's plea to really get to the heart of the confusion. Then we'll build a super solid foundation by nailing the difference between accuracy and precision. From there, it's all about the official rules for handling your numbers, the math behind combining uncertainties, and finally, we'll pull it all together so you can walk into your exam feeling totally confident.
Okay, so first up, let's unpack all that confusion. You know, the biggest problem isn't that the rules are all that complicated. It's that students get so much conflicting advice that they start to second-guess every single number they write down.
And this is the core of the problem, right here. This comes straight from that student's post. On one side, you've got Rule A telling you, hey, uncertainties are always one significant figure, and all the values in a table column have to have the same number of sig figs. But then you've got Rule B saying, hold on, the uncertainty actually depends on the original value, and table columns need the same number of decimal places. So which one is it? It's no wonder everyone's confused. To figure this out, we've got to go back to basics.
Right. Before we can settle that whole debate, we need to build our foundation. We have to talk about the quality of our numbers. And this is all about accuracy versus precision. They sound kind of similar, but in physics, believe me, they mean very different things.
First, we have random error. Just think of this as the unpredictable wobble in your measurements. Maybe it's a tiny change in the room temperature, or just your own reaction time with a stopwatch. It causes your results to be scattered all over the place, and that really messes with their precision. You can't ever get rid of it completely, but you can definitely reduce its impact by taking a bunch of readings and then calculating the average. Now, systematic error is a whole different beast. This is a consistent, repeatable error that pushes all of your measurements in the exact same direction. The classic example is a scale that reads 0.2 grams before you even put anything on it. That's called a zero error. This kind of error destroys the accuracy of your experiment, and just taking more readings won't fix it. You have to actually fix your equipment or your method.
So, with those errors in mind, precision is just all about consistency. How close are your measurements to each other? If you measure a piece of wire 5 times and get pretty much the exact same number every single time, then your measurement is highly precise, and that tells you that you have very low random error.
Accuracy, on the other hand, is about how close you are to the truth. How close is your measurement to the actual real value? I mean, you could have a super precise set of measurements that are all totally wrong, just because your ruler was made incorrectly. High accuracy means you have low systematic error.
This table kind of sums it all up, doesn't it? Random error messes with your precision, giving you a wide spread of data. The fix? Repeat and average. Systematic error messes with your accuracy, shifting all your data away from the true value. The fix here? You gotta recalibrate your gear or rethink your whole method. Getting this difference is absolutely the key to unlocking everything else.
Okay, with that foundation in place, now we can finally open up the official rulebook. This is where we get to directly answer those questions that cause so much stress and clear up all that conflicting advice once and for all.
So this is it, the big one. When you're filling out your raw data tables in paper 3 or 5, what's the rule? Is it consistent significant figures, or is it consistent decimal places?
And here it is, the definitive answer, and this comes straight from the Cambridge syllabus, so you can trust it. It says to record raw readings to the same degree of precision. So what does that actually mean? Simple. It means using the same number of decimal places. And think about why that makes sense, right? The number of decimal places reflects the precision of your measuring instrument. If your ruler measures to the nearest millimeter, then all your readings from that ruler should be recorded to the nearest millimeter, or 0.1 centimeters. It's about consistency.
And boom, here's the piece of the puzzle that solves the confusion. The rules are different for your calculations. See, for adding and subtracting, you stick with decimal places. Your answer just can't be more precise than your least precise measurement. But For multiplying, dividing, or using powers, you switch over to significant figures. Here, your answer's certainty is limited by the measurement with the fewest sig figs. So yeah, 2 different operations, 2 different rules. Simple as that.
All right, so we've got the rules for presenting the data. But what about the uncertainties themselves, the whole plus or minus thing? When you calculate a new value from your measurements, how do you figure out the new uncertainty? Let's get into the math.
When you're adding or subtracting values, the rule is actually wonderfully simple. First, you just add or subtract the main values like you always would. But then for the uncertainty, you always add the absolute uncertainties. Yep, even if you're subtracting the main numbers, the potential for error only gets bigger, so you never, ever subtract the uncertainties.
Now, for multiplying and dividing, we have to change our approach just a little bit. You do the calculation on the main values as usual, no problem there. But for the uncertainty, you first have to convert your absolute uncertainties into percentages. Then, just like with adding, you always add those percentage uncertainties together to get the total percent uncertainty in your final answer.
And what about our last case? What if you're squaring a value or taking a square root? Well, you calculate the main value as normal. Then, you just take the percentage uncertainty of your measurement and you multiply it by the power. So, if you square something, you double its percentage uncertainty. If you take the square root, which is just the power of a half, you have its percentage uncertainty. Easy.
Okay, we have the foundation, we have the official rules. Now let's just put it all together into a practical checklist that's going to give you total confidence when you walk into that exam hall. Here they are, the absolute must-knows. Number 1, raw readings in a table. Same number of decimal places every time. Number 2, calculated values. Follow the sig fig rules based on what you're doing. Number 3, if you repeated a measurement a few times, your uncertainty is just plus or minus half the range, half the biggest value minus the smallest. And finally, when you state your final uncertainty at the end, the standard is to give it to 1 or maybe 2 significant figures. That's it. These 4 points are going to handle almost every situation you'll ever face.
You can think about it like this: Newton's cradle. Every single measurement you take is like one of those steel balls. Its precision and its accuracy determine how clearly and reliably that impact travels down the line. Handling your data and your uncertainties correctly isn't just about following rules for an exam. It's about respecting the integrity of your experiment. It's about making sure the conclusion you draw is a real reflection of the physics you're observing.
So there you have it. The conflicting advice is settled. The difference between precision and accuracy is crystal clear, and the rules for your tables, your calculations, and your uncertainties are all laid out. You now have the definitive guide that student on Reddit was looking for. The only question left is, are you ready to use it and become the expert in your exam?